All right, so what we are dealing with is stereochemistry, optical activity, and drugs. And we're going to be beginning with the introduction. Yeah, the chapter one where we have the optical activity and chirality. That was what I just listed to you, the things we're going to cover. Now, with regards to the introduction, let me bring to you the idea of optical activity and drugs. Now, optical activity was already known to humankind from the 19th century. So, but there's a particular drug which actually led to much more interest developing with regards to optical activity. And the drug which I refer to is the drug called thalidomide. Thalidomide. Now, thalidomide happened to be called a wonder drug that was being used by pregnant women to be able to avoid morning sickness. Yeah, during that time. So, and then what happened with the thalidomide saga was that thalidomide was being consumed then around 1954, 60s and the likes. So they were being consumed then by the pregnant women for them to be able to combat the challenge of morning sickness. So, but over time, they did realize that the children that were born to these particular women, they had defects. They had defects like deafness, they had defects like blindness, they have defects like disfigurement. And then because of that, they had to now check what exactly was responsible for it. And they traced it to thalidomide. And this is the interesting thing. Thalidomide happened to have two enantiomers. Thalidomide has the arrow enantiomer, and then it has the S enantiomer. It has the arrow enantiomer and the S enantiomer. And according to the research, they found out that what was responsible for the therapeutic effect, which is the morning sickness resolving effect, happens to be the arrow enantiomer. And what was responsible for the teratogenic effect, when I say teratogenic, I simply mean for the effect it has on the fetus in the pregnant women, was the S enantiomer. So what it simply means is that if you're going to produce a thalidomide that was not going to have the negative effect, which is the teratogenic effect, they have to just get the arrow enantiomer. This particular event with thalidomide led to much more research going on with regards to the optical activities of drug, which is why this topic is being brought to you today. Now, we talked about the arrow enantiomer and the S enantiomer. As we go on in this video, you will get to understand the idea of the arrow and the S. But just to give you a little insight, arrow is from the word rectus, which is right-handed, and it is actually clockwise. And then S is from the word sinister, and it's for anti-clockwise. Now let us look at a clock. I'll just draw a very, very quick clock for us. So this is a clock, and then we have the different hands that are on the clock and the likes. All right, so in a clock, you realize that the clock actually moves this way. So that is actually right-handedness, and that is rectus, and that's why it's called clockwise. And then if you are going the opposite direction, that's S sinister, that is anti-clockwise. What's the idea of arrow and S? What they realize about these drugs is that if you project a polarized light to this particular drug, the drug will rotate the polarized light in a certain direction. It's either it's rotating it clockwise or it's rotating it anti-clockwise. In that way, that was how they were able to get the kind of enantiomer, arrow enantiomer, and S enantiomer. So as we make progress, I'm going to be showing you how all of these things work under this particular topic. So, but before we make progress, I would like to bring the concept of isomerism to you, which is, stereochemistry is a type of we are talking about a type of isomer, which is stereoisomer. So I just want to brief you on isomers before we make progress into the history of polarized light and all the likes. So isomers, what are isomers? Isomer simply means refers to compounds that have same molecular formula but different arrangements. That's simple stuff. It's same molecular formula but different arrangements. And then when we talk about isomers, we have two types of isomers. We have the constitutional isomers and we have the stereoisomers. We have the constitutional isomer and we have the stereoisomer. In this particular tutorial, our focus will be on the stereoisomers. So, but then for just emphasis, so that you can just brush yourself through with the normal chem which you have had. Constitutional isomers, we have things like chain isomerism, we have things like position isomerism, we have things like functional isomerism. While for stereoisomer, we have things like configurational isomerism, and we have things like conformational isomerism. When we talk about chain isomerism, we simply refer to compounds that have the same molecular formula, but the difference they have is in their chain. Just for want of clarity, I'll be giving individual examples to these isomers which we are talking about. For example, let's talk about the structure of butane. This is butane. Butane has 4 carbons, and then we have hydrogen all around. This is butane, and butane has a molecular formula of C4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. C4H10. This is the molecular formula for butane. We have C4H10. With regards to chain isomerism, when the chain is the difference in the whole of the structure, that is what we refer to as chain isomerism. So we also have what is something like this. Let's look at something like this. All right, so let's look at this. This is hydrogen, hydrogen, hydrogen. This is hydrogen, hydrogen, hydrogen. And then we'll have hydrogen, and we'll have hydrogen, hydrogen, hydrogen. So what we have here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we still have 4 carbon. This is still C4H10. So, but why this is called butane? This is actually 2-methyl propane. So this is butane, and this is 2-methyl propane. So the kind of isomerism we have here is chain isomerism, because the difference between butane and 2-methyl propane is actually the chain, where you now have a methyl group on the carbon number 2, which is 1, 2, 3 on carbon number 2. I don't know if you're following me. All right, so the next one we're going to talk about is positional isomerism. Positional isomerism just simply refers to like the position of any attachment or ligand, anything at all, to the chain that you have there. A very good example we're going to be using is going to be chloropropane. We're going to be using chloropropane for that, and I will just have to use this particular structure for that. We're going to use this particular structure for that. So yeah, we can have chlorine here. We can have chlorine here, and then in another structure we can have our chlorine. We can have our chlorine here. So we can have our chlorine here, and we can have our chlorine there. So if we are saying, if we are having our chlorine here, we have to call this on carbon number 1, 2, and 3. So this is going to be 1-chloropropane. Why is it called propane? Because it has 3 carbon atoms in the longest carbon chain. Why for this? If we're having our chlorine here, we are going to call this 2-chloropropane. I'm going to call it 2-chloropropane because the chlorine is on the carbon number 2. So this 2-chloropropane and 1-chloropropane, the difference that they have is with regards to the position of the attachment. So that is going to be positional isomerism. Another type of isomerism we can have is the functional isomerism. And functional isomerism just simply refers to like the functional group that is available in the particular compound. For example, we're going to be using ethanol as a very vivid example for this. All right, so this is the structure of ethanol. Is C, then we have our H, and then we have our OH, we have our H. So this is actually C2H6O. All right, so this is our ethanol. This is ethanol we have right here. And then we can also have a compound like this, where we have COC, then we have our H. And what is this called? This is actually methoxymethane. This is actually an ether. So methoxymethane is also having 2 carbon and 6 hydrogen and then 1 oxygen. So what we have here is an alcohol group, and what we have here is an ether group. 2 of them are having the same molecular formula but different functional group, and that's what we refer to as functional isomerism. Then coming down to stereoisomers, we have configuration, we have conformational. In subsequent topics, we're going to be talking about the conformational type of isomerism. It's a whole lot, so we can't be able to analyze that in this particular video. So, but then let's come down to the configurational. In configurational isomerism, we have geometric isomerism and we have optical isomerism. In geometric isomerism, you get to have cis and trans, and you also get to have E and Z, all of these things will be looked at in our particular video. Why I had to do this is because this is our focus for this particular course. Our focus on stereoisomerism. So we'll not do so much on it because subsequently you get to have more knowledge about it. Then under optical isomerism, we have diastereomers and we have enantiomers. So we're going to be moving down to the history of all of this, and we're going to be making progress in this video.